Hi, starting from this week, we will discuss software modeling and the unified modeling language, the UML. We are going to spend 3 weeks in this topic, so this is one of the most important topics in our class. And I show you these slides in the first lecture and showing what is modeling before we build the real thing. And here, before we build the bridge, we have the design of the bridge on piece of paper. So this is called the blueprint. And then this is one of the model of the bridge. Of course, just by looking at this model, we know the the length of the bridge and the height and the distance between the seams, so that we have an overall picture like what the bridge looks like. And then we know the engineering model is a reduced representation of some system. Just by looking at this real system, you cannot tell what's the function and what's the doing of this system. But looking at the model is a reduced, we call it a simplified representation of the system. We just leave out the irrelevant details, just focusing on what element is in here as their connection. Then here is much easier to understand the functionality of the system. So the purpose of any engineering model is to help us to understand the complex problem or solution, and also we can use this model to communicate with other peers, other engineers, and also we can use this one to drive the implementation in our software engineering. If we have, for example, a class diagram, you can automatically generate some code. So that's it's very handy by using the model. So the modeling consists of building. So in order to have this model, we have the we have the modeling activities to build the abstraction of the reality. And the abstraction, of course, does simplification because they ignore the irrelevant details and only focus on what you are interested in at this point. For example, like here, we are just interested in what elements are included, and we don't consider how, in the real time, how they communicate with each other. That's another set of modeling. So here we are focusing on a static model. So you will see that each model has a unique angle, a unique view into the system. So this means what is relevant or irrelevant depends on the purpose of the model. Like so at this point you are working on a structure, or you are working on some dynamic interaction between the element. So this depends on the purpose. You only focus on what is relevant. And why do we model? Yeah, but there's a number of advantage by using the model before we build the real system, because it's much cheaper to mess up the model instead of the actual product. Once you commit a full resource into the product and find out the final product is not what you want, there'll be a lot of loss. However, if just a model, then you can just redesign. Usually when you have a model, we have a review. Review the model, and then you will see that it's much easier to modify the model instead of actual product. And also the model helps us to understand, and also the model can help us to catch the big issue earlier, because when you review and analyze the model, you can catch a lot of mistake. Yeah. Then let's see why we model software. So the model is a simplification of the real system. So the software model is also the same nature, to reduce the complexity. And we know the software become increasingly complex. Like the Facebook has more than 62 million lines of code. For this amount of code, no one can manage this amount of code so to understand the code, even to understand the subsystem or the module you are working on, you still need some model to help you. And we know the code is not easy to understand, not just by the developer who didn't write it, even your own code. You write the code, and a couple of months later, you come back to read your own code. It's kind of difficult. So let alone the code developed by somebody else. So we need a simplified representation of the code. So model is a way to do that. And we know that the model we are dealing with are all visual model. There's two kind of model. One is we call the textual model. For example, like the source code is textual model, and the class diagram is a visual model. In the source code, just by here we have 5 classes involved. Then even we put them in one page, you still I mean, it's still not easy for you to understand the relationship of this of the 5 classes. However, uh, if you put them into a UML class diagram, you will see that yeah. So just by looking at the class diagram, you can easily tell what data is manipulated and what operations can be requested and how each of the classes related to each other. So in here we see that both IDAP and the object map class manipulate the instance of the object object value class, and you can also tell that IDAP status class is only interested in the object map, and this SZDB classes by definition it has no relationship with any of the other class. So here you can tell the relationship and what the method and what the data are transferred back and forth between the class. So that's an advantage of visual model than the textual model. So all the UML model we are dealing with belong to this category, the visual modeling. Then let's see what is UML. So first of all, UML is a language, not a model. So UML is a product and is from the object management group and is published as a standard. Therefore, it is open source. So the goal of UML is to provide a standard notation that can be used by all object-oriented methods and to select and integrate the best element from other notations. For example, like UML include the use case diagram introduced by the object-oriented software engineering, from that textbook, and use many features of the OMT. The object modeling technique. There's a book published in 1991 that the feature of the class diagram and the UML also includes some new concepts that were not presented in other major methods, and such as extension mechanism and constraint language. So UML has been designed for broader range of applications. So you'll see that UML is quite powerful. However, before UML became the standard, and back in the 80s, there were many modelers fighting the method war, and each warrior developed his own approach to software system and engineering design. And UML is the legacy of the war and a war that occurs as a fusion of several computing methodologies. And eventually the UML won the method war and become the standard. And the UML goes through different versions, and now the current version is 2.51, and this introduced in December 2017. So this gives you the history of UML. In March 2003, the UML 1.5 introduced and very popular. And 2 years later, there's a major upgrade. It's from 1.5 to UML 2.0. So this is a major upgrade, and there's a lot of new things and new constraint implied, and I will show you in the next slide. So this is a major upgrade, and then since then, since UML become a standard, has been widely used, it's better not to change the standard so often. So you'll see that after that, the upgrade of the UML become slow. 2011 UML 2.4, and 6 years later is UML 2.5.1. So each version has a slight, I mean, yeah, have some update, but not significant, not as significant as from 1 to 2. Okay, let's see what's the new themes in the UML2. The first, the message can be lost and it can be found, and this is a big deal. Yeah, think about this. In the past, the message you may have a different interpretation in different model. For example, like in the class model. In the class diagram, the message is called the function call. When the class A communicated with class B, then class A hold a reference to class B, and then class A can call a method in the class B. Then, so that function call is called a message. So for every message, there's a sender and there's a receiver, and the message can be lost. Means you can send the request to a class that you don't know in advance, and that's very common in the OO design. For example, if you in the future, if you take my design pattern, you will see that there's a chain of responsibility. It shows that there's a number of classes that can be that can answer the call from another class. So from that class point of view, the message, the request is sent to the chain, but that class doesn't know which class actually answered the request. So from the sender point of view, the message is lost, or there's a uncertain receiver. So on the other hand, from receiver point of view, we try to decouple the system, because in the old design we try to minimize the coupling and increase and maximize the cohesion. So when you minimize the coupling, we try to decouple the sender and the receiver. So in many cases, the receiver just take the request, but may not care who sent the request. So from that point of view, the message is can be found. Yeah, it's like, which means there's unknown sender. So the message can be lost and found is a big deal in the UML the version 2, because it's fits well so much in the OO design. And also sequential diagram can capture conditional and looping logic. So usually in the sequential diagram, like the sequence diagram, they don't have this conditional and the looping. So by introducing this, can increase, can make the UML more flexible. And also eliminate the discrete value, and here in the UML2, usually they just give a range. But the discrete value they believe is kind of redundant, so they remove it. So there's some other features as well that in the UML2 they make change. And also in the UML2, they have like a frame for every diagram is put into a frame, so that you can increase the readability of the model. And change in the diagrams notation, like the activity diagram, deployment diagram, sequence diagram, they have changes in there. So we'll get to there when we'll get to change when we discuss the detail of these diagrams. Okay, let's see the notation for all UML2 diagram, but now the frame is now mandatory. Yeah, the frame is mandatory, and then the frame has a heading. The heading contains the type of diagram, the name, and any parameters included. So and also here are the diagram kind. So this diagram kind is coming from here. So for every diagram, there's a two or three character, there's three or two letters showing the type, like the ACT for the activity diagram. So when you see this ACT, then you know this is activity diagram. And then CMP stands for component frame, and SD stands for interaction frame. So why SD stands for interaction? Because SD stands for sequence diagram. In the past, we called it sequence diagram, and people already used to this. The name. So suddenly, if you change, to a different type, people get unused to. So we still use the SD, for the interaction frame, and the package PKG for the package frame, and the STM is a state machine, and the UC standing for use case frame. So for each frame, and we have this type to represent the type of the content in this diagram. Then in the UML, there are so many diagrams. We don't do all of them because that were too much. So we only focus on the 20%. But based on this, so usually, in a modeling system, we can have 20% of the product account for 80% of the profit. So we apply this principle. We only focus on this 20%. However, we can use this 20% of model diagram to solve most of your need. So this gives you the overall diagrams. There are two major type: the structure diagram, talking about the statical structure of the software system. There are class diagram, composite structure diagram, component, object, deployment diagram, package diagram, and there's another aspect of the diagram answer the behavior. We call it dynamic behavior of the software system. The activity diagram, use case diagram, state machine, and the interaction diagram, including the sequence, interaction overview diagram, communication, and timing diagram, in which the diagram in red are new in UML 2. Okay, so you may ask why we need so many diagrams. Because the answer is very simple. Because a system typically has many stakeholders. For example, like you have a customer, you have a domain expert, you have business analysis, designer, marketing team, sales team, product manager, programmer, database administrator, and then this list can go on, like people working on the maintenance and the testing group. There's so many stakeholders. Stakeholders are the person who are interested in your system. They have some kind of relationship with your system. So each stakeholder has a unique view, has a different view of the software, and they have a different background. They have a different background, different interest in different angle. So how can you communicate among different stakeholders? So that's why we need so many diagrams, and each one focus on one aspect of the software, so that we can satisfy as many stakeholders as possible. So this gives you the UML diagrams we will discuss in our lectures. We will discuss use case diagram, class diagram, sequence diagram, Statechart, activity, deployment diagram, and the requirement diagram. So in here, the use case diagram describes the functional behavior of the system as seen, from user point of view. So here is an example of the use case diagram. So when we, the starting point of the software development is the software requirement. So the software requirement is the joint effort between the customer and the software engineer. But these two group has different background. And for example, like you as a developer, you understand the developing philosophy and technology, like the database, you know the testing, and you know how to write the code, you know how the subsystem and the classes communicate with each other. And the last few weeks we know how to how to use a Git and a GitHub and continuous integration. These terminologies are all new for the customer. Yeah, they don't understand that, but they have the application domain knowledge. For example, like if you are asked to write the code to develop accounting software, and but you have no accounting background, but your user, I mean the customer, has a strong accounting background, and they know like how the accounting work, but you have a solution domain knowledge, and this use case diagram can bridge the gap between the people with different background, because this use case represent the functionality of the system from user point of view. Class diagram. Class diagram represent the structure of the system. So what I show you here, not only showing you the class name, I also show the attribute and the operation, and these connections shows that the classes has a relationship, and you will see that there are different kind of connections, and each represent a specific connection between the classes. Like this one is showing the inheritance, and it shows that this beverage, this base class. Then we have espresso and that decorator. They're both special. They're both kind of beverage. And here is the aggregation. Yeah, the decorator consists of the beverage. So you'll see that these two classes has two relationships. One is the inheritance, and they also have the aggregation. So the class diagram not only show the class detailed class information, and also show the connections between the classes. And once we have this class diagram, there's many UML tools can generate the code based on the class diagram we provide. So that's very handy. So in all, the class diagram represent the structure of the system, and there's different levels class diagram you can use. You can use a domain level class diagram. That's in the earlier phase of your design, when you don't have much information about the system, but you still can come up with some class diagram on the top level, and eventually each class you define in the domain level can become a subsystem, or component. And then we have analysis level class diagram. That's one when we're working on the requirement, and during the requirement analysis phase, we do the requirement, and at the same time we do some kind of design. So in that phase, we have the we have an analysis level diagram. So the class diagram in that phase contain more information, just the name. For example, it may contain some attributes, and then we have a detail level design. Detail level class diagram. So what I show you here is actually the detail design level. This is focused on one individual component or subsystem, but we have everything. Yeah, we have a class name, attribute, and operations, and also the connection between them, and the connections will be down to the detail of the different connection type. So this is a detailed design level. So the class diagram can go through from domain level, analysis level, and the detailed design level. And we will practice that when we get to the class diagram. Okay, sequence diagram represent the behavior as interaction. It shows the interaction between the object. So here each message here is a function call. Like the create contact. Create contact is is one of the methods in the view contact list object. So in here this the object, they have a different looking, and this shows that there are different kind of object. So the object with a vertical line, we call this as a boundary object, and This one we call is a control object, and the one with a horizontal line is an entity object. So here for any sequence diagram, there are three objects involved. Usually three objects involved: the boundary, control, and the entity. So we'll get to the detail of this. I think in the future. And the state diagram focus on individual class or individual subsystems, and it shows that for complex object they have different state, and the event may trigger the object change from one state to another. So here we have a Statechart diagram to illustrate how this state change back and forth and driven by the event. Activity diagram is used to model the flowchart or the algorithm or the functionality between the use cases. And here there are many conditions, looping involved, and also we apply this swing name. So in here we have the horizontal swing name. We separate the activity diagram into the top and the bottom, and in here we see that we have the object order and the transaction. So in here it shows that these activities are the order's responsibility, and the transaction is responsible for the send invoice, process payment, and the customer payment activity. So in here we can separate by the responsibility by using this swing name. So in here we don't change the activity diagram, we just reorganize them so that it is clear to tell who is responsible for what. So this activity diagram is very useful to analyze the software. And also we have a deployment diagram, and this models the runtime architecture of a system, shows the configurations of the hardware element, and the hardware element are showing as a node, and show how software element and the artifact are mapped into this node. Show how and where system will be deployed, and the physical machine and the processor are reflected as a node. So here, and the internal construction can be depicted by embedded node of artifact. So this is a deployment diagram, and we'll discuss this in detail. And the requirement diagram. So the requirement diagram is to describe the system requirement or features as a visual model, and the requirement element may then be linked back to use case and the component in the system to illustrate how a particular system requirement is met. And the requirement model enable for traceability between the specification and design requirement and the model element which realize them. So here the requirement model focus on the traceability, and also the requirement the diagram shows the relationship between between the requirement. For example, okay, hold on, let me turn on the camera. We know the requirement document is written in this hierarchy. Requirement 1, it's not focused. Hold on, let me adjust the focus. Okay, now it's better. Okay, so this is requirement 1, and then you have requirement 1.1. and the requirement 1.2 and the requirement 1.3, and of each line is a requirement. And then you have another hierarchy. Requirement 1.3 is a requirement 1.3.1, and requirement 1.3.2. So you'll see that the requirement, if you put them into a tree structure, they have this structure. However, you won't so here the requirement one contain this many detailed requirement, but you cannot tell. But this tree structure doesn't tell you that if the requirement 1.1 and the requirement 1.1 1.3.1 they have some connection. Yeah, they have some connection. Then how we model that? Then we can use the requirement diagram to show they have connection. They have connection. So in other words, if they have relationship, they have some kind of connection. If you make change to the 1.3.1, and then you may also need to go back to the 1.1 to take a look because these two are related. So the requirement diagram, then the hold on, let me see here. Yeah. Yeah, if you change one requirement, you need to go back to check the related one. Yeah, so this requirement model can so once we define their relationship, then we can, when you change one, then you know what else we need to check. Now let's go to the UML tools. There's many UML tools you can use, and this Star UML. Star UML, you can go to this website. This one is open source, is a very powerful UML tool, and is free. And this Brillo, and this one can be is also I think this one is open source. I'm not sure, but this one is a tool can be used in different in the Windows and in the Mac machine. So this one support multiple platform and a Visio. And here I ask you to install the Visio and Enterprise Architect. And Eclipse has an add-on. You can, if you write the code, and then the Eclipse has a UML designer. Yeah, so here then this one is open, also the open source, and it will draw the class diagram for you. Yeah, so here once you have your source code, and then the Eclipse UML designer can extract the class diagram from the source code. So this one is also very handy if you use Eclipse. Then you can install this add-on. So when you write the code, then you can show the relationship. So what we will focus on is Enterprise Architect. So here, please install the Enterprise Architect. I already posted on the Canvas of the first week. So let me know if you have any issue installing this software, because in the lab in the lab 6, 7, and 8, and also in your final exam and in your term project, you're going to use Enterprise Architect extensively. Okay. Okay, we finished the first topic of today's lecture. The second topic is the requirement and the use case modeling. So first, let's look at what is a requirement? The requirements are the description of system service and the constraints that are generated during the requirement engineering process. So it may range from a high-level statement to a detailed mathematical functional specification. So from the definition of the requirement, we see that the requirement may go through different level, the high level and the detail level. So that's we call it two type of requirement. One is a user requirement, is a statement in natural language plus some diagrams of the service and the system provide, and its operational constraint written for customer and sometimes provided by customer. And the system requirement is a structured document setting out a detailed description of system function, service, operational constraint, define what should be implemented. So may be part of the contract between client and the contractor. So you will see that the user requirement is in a higher level written for the customer, and sometimes customer also provided some part of the user requirement. The system requirement is for the engineer to conduct engineering work. So these are two levels of the requirement. In here, this gives you the example of a user requirement and the system requirement. So from here you see the user requirement. The system shall generate a monthly management report showing the cost of drugs prescribed by each clinic during that month. So just by reading this requirement, we can understand what a user try to do here, but the lack of a lot of detail. For example, like the monthly report. So when should we generate the monthly report? Is the last day of the month or first day of the month? You know, the timing is not clear here, and also showing the cost of a drug. But should we just show the cost of a drug, where other information be included in the report? Yeah. So you see that this user requirement, we know generally what the user try to do here, but we don't know the detail. So the system requirement will dig into the detail that what the user really want. Yeah. So here from this one user requirement, we have this more than five system requirement. The 1.1 and the last working day of each month. So from here, see that the monthly, be more specific, is the last working day of each month. A summary of drug prescribed, their cost, and the prescribed clinic should be generated. So you see that contain the content of the summary. And the 1.2, the system should automatically generate the report for printing after 5:30 p.m. So this one is down to the time. The first one shows the which day of the month and what information should be put in the report. And the 1.2 shows the detailed timing. So here, the 5:30 p.m., then it will be much easier to write the program. Okay, after 5:30 is a cutoff time to generate the report. So from when you write the code, then you know what time you put in there. But from the user requirement, you cannot tell this information. But the question is how you get this information from. So here you need to further communicate with the customer to dig out this detail. And the 1.3 is to show the detailed report. Yeah, in here just showing that I want the customer says I want the report, and then you need to ask a customer what information I should provide it in the report. Okay, then a report should be created for each clinic, and it shall list individual drug name, total number of prescription, the number of doses prescribed, and the total cost of the prescribed drug. So in here, detail the content that should be put in the report. And 1.4 is, also here, since we show the number of dose, and then if the dose use the different unit, if the dose are available in those unit, and separate report should be created. So of course, this 1.4 is the one you communicate with customer, and then you catch that information. If there's even you provide the report, but there's a need the customer want, for different dose unit, they want a different report, then you put it in the requirement. And 1.5, access to all report shall be restricted to the authorized user listed on management access control list. So this information and this 1.5 is not part of a user requirement. So a user sometimes, when they tell you what they do, they don't consider this a security, security factor. But you as an engineer, you know that, okay, since I have a report, should the report open to public, everyone has access. If you ask a user this question, then you say, oh, no, this report is not for the public, it's only for a certain member. Then you can have this 1.5. Then you say, okay, who has access? Then the user will give you the list, and then you put them in the access control list. And then of course, for the different user, then they may have a different user level. Like for example, like the manager can view and print and edit, and for the clerk, I mean for the regular user, they can only view, they cannot make a change. So somehow, even for the report, since you can have different control, that's a 1.6, 1.7. So you will see that from one user requirement, only give you the rough idea what a user try to accomplish, but a system requirement down to the point where you can start to design the software and write the code and then come back to do the testing, and so that you test against the requirement to make sure that you finish all the requirement. So here you see the differences of user requirement and system requirement. Then let's go back to our lab. I posted a lab today, so you can take a look of this lab. So lab is due on Thursday on 5:45. So in here, what I give you the customer description of the desired software. So this is the user requirement. You consider this as a user requirement. And then the first task of the lab is choose one user requirement and expand it to a system requirement. And your expanding rate should be at least 1/3. So which means like you choose one user requirement, you expand to at least 3 system requirements. Like in our example here, the one system requirement has 5. So it's easy to generate, for any requirement I listed here is easy to generate into 3. Okay. Yeah, for example, like in here, the eGuide should allow parents to check web activity, keystroke, chat, email, IM, and launched application. So like this one, each one of them, like check web activity is you can consider as one system requirement. Check the keystroke, can be another system requirement, and then you can further dig down into the web activity. So how to check what should be included in the checked activity. Like should I want to check the web activity? Should I check like where I mean the link the link the user the child click and the website the child try to access. So this so when you detail to the web activity, you will see that there's a lot of information behind that you can further expand your system requirement. Okay, like the eGuide should allow parents to configure the setting. The setting include the blacklist, the whitelist. So the blacklist and the whitelist is easy to understand, and the internet time control. So internet time control is a very general term, but when you dig into the detail, like the time control, you should time control including the weekday, weekend. I mean, all the weekdays the same, or like a weekday, I also down to the Monday to Friday, and each day they have you can have a different time control, or just a category, apply to all the weekday and apply to all the weekend. This kind of how detail go to the time control, you can discuss with the customer. So of course in this lab, you play dual role. You are both customer and also you are the engineer. So basically you ask yourself, you come up with this like the internet time control, how detailed you go to. So anyhow, that for any of the user requirement here, it's easier. I think it's quite easier to expand to a 3 system requirement. You can take this as an example how to expand. And then once you have these 3 system requirement, I want to draw the use case diagram for the requirement in the step 1. So yeah, I will get to the user requirement very soon. And then you have a use case scenario description for at least one use case. So here, I will get to 2 and 3 later today. Okay, let's go back to our differences of user and the system requirement. So this is one way to classify the requirement by the levels. I mean the detail you provide, user requirement and system requirement. There's other way to classify. Yeah, I will show you later. Okay. And then let's see the requirement engineering we consider the requirement is engineering work. It is to assist a software engineer better understand the problem they will work to solve, understand the business impact, and understand what the customer want, understand the user interaction with system, and understand the project scope for preparing the project plan. So actually, this one is requirement engineering is a very important work, and this is a starting point of the software project. So if there's a mistake in the requirement, that has a profound impact into the software, into the software product. So it means the requirement mistakes are very expensive. Yeah, it's very expensive to change. Has been probably the most neglected activity of the software engineer. So this one is we know is important and it has a profound impact, and we should pay attention. Yeah. So this shows you that what requirement engineering fit into the overall life cycle. Okay. And also the requirement engineering has two activities: requirement elicitation and the requirement analysis. In here, the requirement elicitation is to communicate with customer and come up with the requirement specification, the system requirement level. And then the requirement analysis is to do some kind of analysis of the requirement, and then it will also back and forth. So this is a loop between the requirement elicitation and the requirement back and forth will make change to the requirement. So this shows you that the requirement elicitation here, the meaning we are dealing with a use case model, and during the analysis we have application domain object. So here, and then system design we have a subsystem, and detail design we have the design level class diagram. So you see that from here we see the class diagram goes through three phases: domain level, analysis level, and detail design level. Okay, and in the requirement elicitation, we are mainly focused on the use case model, and we use this one to bridge the gap between the user and the software engineer. So we know that the requirement elicitation is a very challenging activity because we need to collaborate with people with different background. As I mentioned before, the user has application domain knowledge and developer has solution domain. So this you have two domain knowledge, and to bridge the gap, we use the scenarios and the use cases. So scenarios is an example of the use of the system. Sometimes we just ask a user to tell the story and how you what's your daily operation. Just give me a concrete example how you operate, and then from the scenario, if from the multiple scenarios we can come up with the use case. Use case is abstraction of the scenario. So to come up with a use case, we have two approaches. So one is when you have a multiple scenarios, so you abstract from the similar scenario, come up with a use case, or you can just you can have a vertical slice, go down to the deep of the scenario, go deep and to provide as much detail as possible, and then you may come up with multiple use cases from a single scenario. So there's two ways to come up with the use cases. So let's look at what is use case diagram. A use case diagram consists of the actor and the use cases. In here, the actor represents a role. That's a type of use of the system. So basically, the actor is outside the scope of the software. and the use case represent the sequence of interaction for type of functionality. For example, in here, the passenger is the actor, and the purchase ticket is the use case, and the passenger can purchase a ticket. Yeah, so here the purchase ticket is a use case. What you see, on the surface is just this oval shape, but the use case is more than a oval shape. When you double click on this purchase ticket, in any UML tool, it will pump up a window ask you to enter more information. So what information what information we should put in here, I will show you later. First, let's look at the actor. So we know the actor is model's external entity, which communicate with the system but not part of the system. It's outside. It can be a user, can be another system, can be the physical environment. That's anything that outside the system that may have connection, that may have interaction with your system, can be considered as an actor. So a use case, as I mentioned, is not just an oval shape. The use case usually contain a name, contain the participating actor, and it will show who will interact with the use case. It has entry condition and exit condition and flow of event. So basically, the entry condition is a precondition. So what a user should have to operate operate this use case, and the flow of event is the interaction. Yeah, this one, the flow of event is the meat of the use case. So how you get the flow of event? So here you need to communicate with the customer to figure out the step-by-step operation this use case happen internally. And then exit condition is after. So given the entry condition, after you have this event happen, what's the result? Is the exit condition. And a special requirement is for the use case. So here you have some constraint. So here usually is a performance issue. For example, like a purchase ticket. How like for each step. Yeah, for each like for example, like a customer click on the purchase ticket button, how long the system should react. Yeah, should display things in less than a second, will take like 5 minutes to show the result. No, that's not making sense. So somehow you need to have some performance issue, like you can specify here, and eventually this is a special requirement here. We will become the non-functional requirement later on. So here we start to think about the performance, the security things, issues when we're dealing with the use case. In previous example, let's show the use case diagram example. The name is the purchase ticket, and the participating passenger actor is a passenger, and entry condition is a passenger standing in front of ticket distributor. So show that the passenger has access to the distributor, and also the passenger must have enough money to purchase ticket. And exit condition is after the operation, the passenger has a ticket, and the event of float. So this tells you the detailed steps the passenger will go through in order to get the ticket. So the first passenger select the number of zones to be traveled, and then distributor display the amount due. The passenger insert the money of at least the amount due. The distributor return change, and distributor issues ticket. So from here you will see that a use case is a single usage of the system. There's no like if and then, and a loop. These things happen. So it's one clear-cut usage of the system. And just by looking at the event of flow, then you may think of this. Well, this may have some exceptional case happen. So what if the passenger standing, just choose a zone, and once the distributor display the amount of due, and the passenger find out doesn't have enough money, then the passenger just walk away. Then where the machine here just hanging on there forever, that doesn't make sense. So this must be a timeout issue. Yeah, there must be a timeout mechanism. If the passenger walk away without hit the cancel button, and then the distributor will wait some time and then will cancel the transaction. So you think of, there's a lot of the exceptions can happen here. And what if the passenger insert the money and this money cannot be recognized, like like the when insert the coin, when insert the quarters, if the quarter is too old, the distributor cannot recognize it, and what should be done. So in here you see, for each step, there's some exceptions can happen, but we don't include it in the use case here. And then how can we model the exceptions? So this we call the related use cases. We can use the extend relationship, and this one to represent the seldom invoked use case or exceptional functionalities. And also, can we have a include relationship? Yeah, I will show you this one later. Let's first look at this extend relationship. So here we have a purchase ticket. In our previous example, we show you that in the flow of event, you see that some certain step can go wrong. Like out of order, yeah. If the distributor make out of order, okay, and cancel means the passenger can cancel the transaction anytime he wants. So what if the passenger click on the cancel button, and no change? What if the distributor run out of change? And of course, will issue ticket, and the distributor can also run out of paper. So this a lot of things can go wrong. Then that exceptional case are extended use case of this purchase ticket, and of course the timeout. And we already talk about this timeout, and also the extended test case, the extended use case of the purchase ticket. And then the include relationship represented one use case explicitly include the behavior of another use case. So usually when we have a multiple use case involved, similar use case involved, then we can abstract out the common path and form a new test case, and that new test case has an included relationship with the other test case. For example, like here, the passenger can purchase the different ticket, can purchase a single ticket, can purchase multiple card, and then maybe if you keep going, the passenger can purchase a weekly pass, and some passenger may purchase a monthly pass. So here you have a different purchase option, but no matter what purchase activity you have one common activity is called collect money. Yeah, so we can abstract this collect money out and form a new test case, and a new use case. That this new use case is focused on one activity, just to collect money. So so once you have this include relationship, we increase the readability of the use cases, and also this will help us later on in design the software. When we so here we can have one subsystem just focus on the collect money, so it will help us to design the software as well. So here we have a two relationship. One is extend to represent the exceptional, and also we have included to answer that if you have a common activity and want to factor out. And the use case diagram can also be similar, very much like the class diagram. You can have a hierarchy. So you can have a parent's use case, you can have a child has the use case. The child has case is a kind of, and to represent a kind of relationship. Let's work on this use case example. So here I want you to draw a use case diagram for ticket distributor for train system. The subsystem include two actors, a traveler who purchased different kind of ticket, and a central computer system which maintain a reference database for the tariff. And here the use case should include by one-way, bi-weekly, bi-monthly, and update tariff. So here we have 4 use cases, and here we have 2 actors, traveler and the central computer system. So here also I want to include the exceptional cases, the timeout, transaction aborted, and distributed out of change and out of paper. So here we have 1, 2, 3, 4. We have 4 exceptional cases. You will see that these 4 exceptional cases apply to 3 purchase activities. So here we have 3 purchase, and each of them has 4 exceptional cases. So if you draw the use case diagram, you will see that there will be like a 3 times 4, 12 connection. That's that will be too much. 12 connection will make the use case diagram difficult to read. And then what you can do is you can have one exception, distributed exception as a parent use case. Then you have a child use case timeout, transaction aborted, out of change, and out of paper. They are part of there are different kind of exceptions, and then the entire structure here extend by one way, by monthly, and by weekly. So in here we eliminated the needed to connect each purchase to 4 of them. That would be 12 connections. That would be too much and make it quite messy. And the central computer system will interact with update tariff. Of course, from here you will see that the traveler cannot update the database. Only the central computer system can update the price of the ticket, for example. Okay, this gives you the use case, and then let's go back to your lab. So in here, the lab, I want to draw the use case diagram for the system requirement you specify in task 1. And then I want to include the use case scenario description for at least one use case here. So in here, for example, you extend the user requirement into 3 system requirement, and then for each system requirement, you have a use case or a bunch of use cases to describe the system requirement, and then you can choose one use case, and then you put a detail. The detail, what I mean is, you provide the entry condition, exit condition, and the flow of event, especially the flow of event into this one use case. So here you may come up with like 5 to 7 use cases, but you only choose one use case to provide these details. Okay. And then after the lab, so in the lab, since you have only 1 hour and 45 minutes, and I think this is sufficient to finish these 3 tasks. When you go back home, your term project is the extension of your lab. So we'll gradually. So today I will. I don't think today. I think the next week, when we get more into the UML diagrams, I will provide the term project. You will see that your term project is actually the extension of your lab. So you're further working on the lab assignment, and then will eventually become your term project. So in here, the term project, I ask you to add the detail into one test cases, into one use cases, and then please continue adding the detail into the other use cases, because your term project will focusing on the same system, the same software, but I will ask you to provide details of each use cases, and not just use case diagram. In the future, we are going to learn the class diagram, activity diagram, sequence diagram. So you will, all of them will be included in your future lab and the term project. So so you can start working on your term project now. You have to add more detail into each use cases you have in the lab. Okay, let's continue on the requirement. So we classify the requirement in terms of how many information input. Like we have the user requirement and the system requirement. There's other ways to classify the requirement by like the functional requirement and the non-functional requirement. The functional requirement describe the interaction between the system and its environment, independent from implementation. For example, the ATM should provide the cancel button. So this requirement focusing on the system requirement level. So usually in the user requirement, we don't further classify into the functional or non-functional because the user focuses more on the functional part. Yeah. So, but once we get down to the system requirement, we need to classify is the requirement is to describe interaction, or the requirement is to describe the performance issue. You know, so the non-functional requirement is a user visual aspect of the system, but not directly related to functional behavior. For example, like the response time must be less than 1 second, and the server must be available 24 hours a day. So usually this information is not obvious from the beginning, but once we but once we dig down into the system requirement and communicate with customer, we can get this non-functional requirement. Okay. Okay, next let's take a closer look of the non-functional requirement and what are the non-functional requirement? We know this different kind of non-functional requirement you can put in your requirement document. The first one, like the usability, is easy with which user can learn to operate, prepare input, and interpret output of a system. Often client address usability issue by requiring developer to follow user interface guideline on color, logo, and font. So for anything related to what the interface should look like, what warning message should be provided, and the color, these things are all related to the usability. And the reliability is the ability of a system to perform its required function and the stated condition for a specific period of time. Like the software should not fail. I mean, can fail at least can fail at least once or twice in a month, yeah, something like that. Yeah, the robustness is the degree to which a system can function correctly in the presence of invalid input or stressful environment condition. Yeah, for example, like like the cell phone. Yeah, the cell phone can still function underwater. Is waterproof. Yeah, is waterproof. That's is robustness. Yeah, that's a one non-functional requirement. Nowadays, many cell phone can do that. Yeah, and safety a measure of the absence of catastrophic consequence to the environment. Yeah, so these are the non-functional requirements, and also so there's more, and most of them are related to a lot of them, I can say, related to the performance. Concern with the quantifiable attribute of the system, like the response time, how quickly the system should react to certain input, and the throughput, availability, and accuracy. These are all related to the performance. So okay, and then you have things can be concerned with the supportability, concerned with the easier of change to the system after deployment, adaptability, ability to change the system, deal with additional the application domain, maintainability, the ability to change the system to deal with new technology or to fix defect, portability, easy with which a system can be transferred from one hardware software platform to another. So here are also the non-functional requirement you can put in your mind. If you needed to communicate with customer, you can ask this kind of question. Yeah. Okay, let's working on this exercise. So in here, I want you to map these 5 non-functional non-functional requirement to the type of the non-functional requirement. Okay. So this MTTF stands for mean time to failure. The mean time to failure of the system should be larger than 240 hours. Okay, what non-functional requirement it is? It is reliability, performance, supportability, usability. Yeah, this one is the reliability. Okay. When user click on the show status button, the result should be shown in 1 second. Yeah, this one is response time, is a part of performance. The warning message should be in red. So this one is talking about the color of the warning message. So this one is a usability. It's talking about the interface. And the system should display time correctly in all 24 time zones. So what is? Yeah, so this one is actually talking about the accuracy. So accuracy is part of the performance. So this is a performance non-functional requirement. And system should be able to upgrade. So this one is the supportability. Talking about how easy to make change to the software. Okay, so here, so we do this exercise. You see that this if I ask you to come up with a non-functional requirement, you can go back to see the type of non-functional requirement that may involve, and then to come up with your non-functional requirement. Let's see when we write the requirement, we should understand what is a good requirement. And what is a good requirement? The first one requirement states only one thing. Don't try to put multiple items into one requirement. That will only cause the confuse. For example, like here, this requirement talking about more than one thing. The current value representing a deviation larger or equal than 5% from the nominal value shall cause a display on the operator monitor. And if the deviation is more than 10%, and then you will cause alarm sum. So you'll see that this is actually talking about two. You can separate into the two requirements instead of putting them in one. So please make sure that one requirement only states one thing. And it is implementation free. Don't state. You only state what should be done, not how to be done, because how to be done, leave to the developer to working on it. And it must be feasible. It can be achieved and it's attainable. This one is easy to say, but sometimes you may overestimate yourself and put in a goal that you cannot achieve. But that's that's very common in the requirement phase. But so that's why we need to review the requirement to make sure that every requirement item is achievable. And complete should not require further amplification. So this one is also very easy to say. Okay, I know it's very difficult to include everything. If the requirement is complete, then if you can have a complete requirement in the first place, then we don't need any requirement engineering. So the requirement engineering, the whole purpose is to have a feasible and a conflict and a consistent requirement. So these are the quality of the good requirement, but easy to say, but need a skill and experience and need your dedication to make this happen. All the requirement items feasible, and and we leave out nothing, and there's no contradiction, especially when the requirement is come up with the requirement from a team or from different team, then that's easy. You have a contradiction. But to detect a contradiction between requirement needs some additional effort. Okay, let's look at the examples of bad example of the requirement. So this is an uninstanted feature. So the reason they have this uninstanted feature is either the requirement is not clear, were not complete. Some scenario you're not included in the requirement. Well, they have a contradiction. Since this happened, you may have like the unintended feature. So from the news, the London Underground train leaves station without driver, and what happened? Let's see that passenger door was stuck and did not close. So the driver left his train to close the passenger door, and he left the driver door open because based on the training and the specification of the software, they rely on the specification that the train does not move if at least one door is open. However, when he shut the passenger door, the train left the station without him. Why? Because the driver door was not treated as a door in the source code. So somehow, this miscommunication, between the user and the developer, or the requirement itself is not complete enough to show that like the driver door, all door including driver door are doors. So when you write the code, you see that door should also be closed in order for the train to move. And also the requirement must be unambiguous. So one or the only one interpretation. And here we use the word shall to make this one clear. And then the word to avoid that, when you have a multiple interpretation, like the flexible, the fault tolerant, the high fidelity, adaptable, rapid, or fast. So this word, you have different people have a different opinion. So we do not use this kind of word in the requirement. So the requirement must be very precise, and also is testable. So when you write the requirement, there's must a way to verify the requirement is actually met. So when you write the requirement, is not general. Try to have some quantitative number so that we can verify. And the functional complete, not missing the requirement. Okay, let's look at one example of ambiguous specification and what will happen if we have ambiguous specification. So during a laser experiment, a laser beam was directed from Earth to a mirror on the Space Shuttle Discovery. And the laser beam was supposed to be reflected back towards a mountain top 10,023 feet high. The operator entered the elevation of the mountain and the 10,10023, and the light beam never hit the mountain top. So it means you hit the reflection not going back to where it's setting to. And what's the problem? Because the computer interprets the number in miles. So here, supposed to be feet, but when you feed the number, if you don't specify the unit, the computer interprets in miles. So you'll see that when we have the specification, we have the requirement, we need to avoid this kind of ambiguity. So here, when you have, for example, here, when you have the number, if you don't specify the unit, then people have a different interpretation. So in the requirement document, we try to avoid that. We try to just that people has only one interpretation. Requirement tools. There's many tools support the requirement. We know the requirement engineering need the collaboration between different teams, the customer, even the developer internally. You have multiple people working on the requirement. So the requirement tools should support this kind of collaboration. And then, so here we have a Requisite Pro is from IBM. The DOS is a very popular distributed requirement tool. And Enterprise Architect can also support the requirement. So here you can have your requirement document items managed by the Enterprise Architect. You can also draw to the use cases, requirement models using the enterprise architect. So we will be using the enterprise architect. Please install the software and make sure it's functional. And your lab and your term project, you are going to use the enterprise architect extensively in your lab and the term project. Okay, I think that's it for today's lecture. And the TA is still working on your exam, so I think we should have your grade of your midterm exam posted on Canvas this week. Yeah, so please so keep watching this Canvas. Yeah, once the grade posted, if you have any question, please contact the TA first. And if he cannot resolve your issue, then you can approach me. Okay. I think that's it for today. I will see you next week.